When water moves into air-dry soil, it is only slightly affected by gravitation. Water moves upward and horizontally as well as downward. The principles governing water flow are graphically shown in this time-lapse study. In these demonstrations, soil is held between glass plates so that you can watch what happens as the soil is wetted. The glass plates are a foot high and 2 feet wide, with about 1/2 inch of space between for soil. Think of this model as representing a vertical cross-section through the soil. Time-lapse photographic processes used here permit speeding up the action. In nature, it would require many hours to see this action. Here you see it in just a few minutes. Using a motion picture camera, single pictures are taken of the models at short time intervals as the water moves into the soil. The time intervals are from 1 second up to 22 seconds. The completed motion picture film is then projected so that speed-up times in these sequences range from 24 times normal to as much as 500 times normal speed. The speed factor will be observed on a card above the model. Because water movement is usually very rapid when water is first applied and is very slow at later times, the speed-up factor is often changed during the sequence. This will be indicated by changing an arrow on the card which points to the appropriate speed factor. The soil used is an air-dried silt loam which has been passed through a fine screen. Sands, clays, and aggregates made from the soil are used to simulate non-uniformities in the soil profile. Water will be added in a furrow or on the soil surface with this device, which keeps the water level at any desired depth. Before you see the sequences using time-lapse photography, here are 2 demonstrations that illustrate the principle of capillarity. This principle is involved when water moves into dry porous materials. Liquid is pulled upward from free water in the dish into this porous ceramic rod because of the attraction of solid mineral surfaces for water, adhesion, and the attraction of water molecules for each other, cohesion. Adhesive and cohesive forces, then, are responsible for moving water upward against the downward force of gravity. The pressure in the water contained in the ceramic rod above the free water is less than the pressure of the atmosphere. This is called tension. In the second demonstration, water rises between 2 closely spaced glass plates because of the adhesive force between glass and water and cohesive forces between water molecules. The height of rise is greatest where the glass plates are pinched tightly together. The pressure in the water above the free water surface in the container is less than atmospheric pressure and is here again called tension. The higher water rises, the greater the internal tension. Now to the models and time-lapse pictures. Watch as the water moves out from an irrigation furrow. Note that the movement outward is almost as great as that downward. This is added evidence that the force responsible for this type of water movement is mainly due not to gravitation, but to the attraction of solid surfaces. As the soil becomes wetter and wetter, however, gravitation plays a stronger role. And if the soil becomes completely saturated, then gravitational forces predominate. The horizontal layer you see is coarse sand. One of the important principles of unsaturated flow is described as you witness what happens as the wetting front encounters this layer of coarse sand. The pores in the soil are many times smaller than those between sand grains. Water is held in these small pores by large adhesive and cohesive forces. The pores in the soil are like the pores in a piece of blotting paper used to soak up ink. The huge pores in the sand cannot hold water at the tensions which exist in the wetted soil above, so the water does not move readily into the sand. However, as the soil above the sand becomes very wet, the water eventually moves into the sand, just as ink would drip from a blotter which is wet excessively. The sand layer thus acts something like a check valve, holding the water back until the soil becomes very wet and then letting the excess pass through. What happens to water in soil containing a sand layer is typical in principle of what happens to water in field soils where sands and gravels occur as layers in finer soil materials. A great deal of agricultural land is layered in this fashion. In Washington State's Columbia Basin, there exists 250,000 acres of soil composed of 1 to 2 feet of a fine sandy loam overlying coarse sands and gravels. The ability of this soil to support plant growth is greatly affected by the presence of coarse sands and gravels. Because of these coarse materials, the overlying soil can retain more than double the amount of water usually held in a fine sandy loam. This is one of the best soils in the Columbia Basin. Now in this sequence you see a layer of fine clay in an otherwise uniform soil. This clay layer is similar to a clay pan or any type of layer in which the pores are extremely fine compared to the pores in the overlying soil. These layers often restrict rooting depths of plants and are particularly known for the trouble they cause in preventing downward penetration of water. When excess water is added to the soil, water tables are often built up over such layers. If they occur at shallow depths, water tables often rise above the land surface during wet seasons, imposing serious limitations on agricultural use. Despite the fact that a clay pan hinders downward movement of water, it does absorb water readily as the soil above is wetted. Observe the wetting front as it moves into the clay pan. The pores in the clay are much finer than those in the overlying soil, so they can pull water from the soil. Water tables are not built up over clay pans because of inability of water to enter them. Instead, water tables result from slow transmission of water. The resistance to water flow in the extremely fine pores of layers like these is sufficiently great that even over periods of weeks and months, little water is transmitted through them into the soil below. The pores in restrictive layers found in nature are quite variable. They range all the way from fine pores that allow almost no water to pass up to pores that are almost as large as those of the overlying soil. The extent to which downward flow is restricted and water storage is altered depends on the fineness of these pores and the thickness of the restricting layer. This is in contrast to what was shown earlier in soil overlying coarse sand layers. There, the downward movement of water was temporarily checked, but water tables could not be built up so long as the opportunity for free drainage into the coarse material was possible. This model has a sand layer on the left and a layer of coarse aggregates on the right. These aggregates are about the same size as the sand grains, but are made up of soil particles like those of the surrounding soil. The large pores between aggregates are about the size of the large pores between sand grains. Water movement in soil materials which wet readily depends upon porosity and not upon the chemical or mineralogical nature of the soil material unless it influences porosity. Each individual soil aggregate contains numerous fine pores of a size similar to the pores in the surrounding soil. As water approaches these aggregates, note that they wet up as soon as the water reaches them. However, pores between aggregates are too large to hold water at the existing tensions. Hence, they remain empty. All of the water must, therefore, move first through the finer pores of an aggregate and then across the point of contact with the adjoining aggregate. The small number of contacts between aggregates restricts the rate at which water can move. If free water is supplied directly to a layer of coarse sand, water rushes in rapidly, filling all the pores. These are conditions of saturated flow. The moving force is due to positive pressure from the water in the furrow. Under saturated conditions, large pores can transmit water readily, with the rate of transmission in a given material depending only upon the hydrostatic pressure of the water supply. The energy derived from this positive pressure is dissipated rapidly over a very short distance in the fine pores, giving way to absorptive forces in the drier soil. Water moves out into the soil from the sand layer under unsaturated conditions. It is pulled into and through the soil because of the attraction for water of the mineral surfaces making up the fine pores of the soil. The sand in the layer at the left is the same kind of sand through which water is flowing at the right. Here, however, the layer is not in contact with free water or water under positive pressure. The surrounding soil is wetted under unsaturated conditions where the water is present only under tension. This sand layer cannot wet until the water tension in the surrounding soil becomes very low, which means that the soil becomes very wet. As this happens, the layer takes water. Porous materials with very large pores aid in water movement only under conditions where they contact free water or water under pressure. Where water exists only under tension, such materials stop or materially retard water flow. A question is frequently raised. What differences in flow might be expected if underlying sands were moist rather than air dry? Here you're looking at dry soil overlying dry sand on the left and moist sand on the right. Since water movement has so far been detected by observing color change, a different technique is needed to help you see water entering sand which is already moist. A chemical substance has been added to a white sand which, when contacted by added water containing another chemical, will turn pink. The water content of the sand on the right is about the quantity which would be present in a sand just barely wet enough to support plant growth. The presence of some water in the sand should make a difference in the tension when added water enters the sand. It appears here that water will enter the dry sand almost as quickly as it enters the moist. There is a difference in the rate and pattern of water penetration into the sand in the two cases, but in both, the water retained above the sand is about the same. Under many conditions in nature, including situations where artificial irrigation is practiced, sands and gravels lying below finer soil materials are naturally moist. It is also important to illustrate differences among uniform soils with respect to their ability to transmit and retain water, apart from problems of stratification. Note that the depth of penetration at any given time is greatest for the sandy loam, which has the largest pores, and least for the clay loam, which has the finest pores. The finer the pores, the more the rate of water flow is restricted. In this case, the larger pores in the sandy loam do connect with the source of free water. Retention of water after the source is removed is greatest in the clay loam, which has the finest pores, and least in the sandy loam. Despite this, however, the net useful storage is greatest in the clay loam and least in the sandy loam. Although a sandy loam retains less useful water than does the clay loam, it is a good soil in an irrigated area where lack of water-holding capacity can be compensated by irrigation. The infiltration properties are generally good. Clay loams, on the other hand, are often difficult to irrigate because of low infiltration rates. In dry climates where there is no irrigation, a sandy loam would not hold enough water to carry agricultural plants through the growing season. A clay loam, by contrast, would retain more water over a longer period of time. Hence, dryland farming on fine-textured soils is practical. The rate at which water would enter the soil is an important factor to consider when designing an irrigation system or when deciding on cultural practices for use in erosion control. In the demonstration so far, your attention has been focused mostly on the movement of a wetting front. Now, with the aid of a soluble dye, the pattern of water movement back of the wetting front appears. Any water-soluble material which is not strongly adsorbed by the colloidal clay will, if placed as are the dye spots in this demonstration, have the net movement you see here. The dye traces are not streamlines. The reason for this is that the geometry of the absorptive force field responsible for water movement is changing. The dye traces include the effect of any change in direction of water flow due to the development of a non-uniform field. Such a non-uniform field is produced as the two wetting fronts join. In the beginning, the dye moves radially away from the water source. This continues as long as the movement of the wetting front remains radial and uniform. Soluble fertilizer materials such as nitrates moving with the water would trace out patterns like these. The dye traces show the importance of proper fertilizer placement with respect to the position of the wetting stream in an irrigation furrow. Now consider what will happen to the dye spots midway between the two furrows as the two wetting fronts come together. Note particularly the middle dye spot at the same level as the water in the furrows. When the wetting fronts join, there is a radical change in the pattern of water movement. Water continues to move upward into the dry hill above and downward into dry soil below. That dye spot in the middle shows little movement because water flow above this level is upward and below it is downward. After the soil in the hill is entirely wetted, only evaporation will cause further upward flow. Such upward flow is of much practical importance. For example, soluble fertilizers in the upward moving stream will tend to accumulate in the surface out of reach of plant roots. Such phenomena have been observed in numerous fertilizer placement studies. You are looking now at a cross-section through a potato hill. Loose soil thrown up into a hill like this can be difficult to wet because of the presence of excessively large pores. The distance between the top of the hill and the bottom of the furrow often is great, as much as 18 inches in some potato fields. Excessive elevation differences, complicated by increasing porosity from the bottom of a furrow to the top of the hill, can lead to poor wetting of the hilled-up soil. Compacting the hill with a roller at the time of planting, as you see it on the left, can help in two ways. First, the elevation from furrow to the top of the hill is greatly reduced. And second, the slightly reduced porosity will help to increase rate of water movement into the hill. Soil in the tops of many potato hills on farms in Washington's Columbia Basin have been observed to remain dry during an entire growing season. This despite the fact that water has been in irrigation furrows as much as 1/3 of the time. Both yield and potato quality in Columbia Basin soils have been improved when the hills have been lowered and when seeding has been deeper. A practical application of principles of water flow to dryland agriculture is shown here. Water moves rapidly into soil with good tilth. Proper tillage practices on the soil in the center have produced numerous small aggregates which have been stabilized by decomposing organic materials. The resulting large pores, which remain open all the way to the surface, take water readily. Thus, the infiltration rate remains high. The same amount of organic material, when turned under in a layer, does little to improve soil tilth, and, if anything, makes conditions worse. The straw layer, like a sand layer, checks downward flow of water. In this case, not only does less of the rainfall penetrate into the root zone, leaving more water to run on the surface, but wet conditions in the plow zone make the soil even more vulnerable to damage such as that caused by the impact of falling raindrops. Thus, you can understand why soil and water loss by erosion is accelerated. On the right, an irregular channel filled with coarse sand simulates an open channel left by burrowing rodents or angleworms, or perhaps a channel left by decaying roots or straw. Such channels or cracks do not assist in water movement when they are not open to a source of free water. They aid water flow only when they connect with free water at the surface. The principle involved also applies to tile drains. Water can move into such drains only if positive water pressures exist in the surrounding soil. Hence, tile drains placed in wet soil must be located below the water table if they are to carry away unwanted water and make the land tillable. Water moves rapidly down into the soil through a vertical channel filled with coarse organic materials. But this is true only if the channel extends all of the way to the surface. This practice of vertical mulching is now being used in some areas where infiltration rates at the surface are too low to permit absorption of all of the rainfall. A vertical channel is cut into the soil with a chisel-like tool. Then chopped organic materials are blown in behind to hold the channel open. The channel itself has the ability to hold some water, and this permits a longer time for infiltration. Putting free water in contact with the underlying dry soil increases the capacity for its rapid infiltration, and hence surface runoff is reduced. Since the water in the surrounding soil is under tension, none has entered the straw channel on the right. The important point to remember here is that the channel must remain in contact with free water or water under positive pressure to do any good. And if the top of the channel is covered over or becomes plugged with fine soil, water flow into the channel is restricted, even though the soil might be saturated. These demonstrations emphasize the principles of water flow under unsaturated conditions, conditions under which crops are grown on agricultural lands. Each demonstration has its counterpart in nature, except possibly this last one. In nature, the demonstrations may be less dramatic, but the principles hold and can be seen in operation if one observes carefully. In summary, then, unsaturated flow of water in soil and other porous materials takes place because of the attraction of solid surfaces for water and of water molecules for each other. How the water moves depends upon the nature of the pores and porosity changes in the porous system.